I think you're on mute.
We can't hear at all.
All right, let's try one more time here.
Yeah, we can hear you now.
I appreciate that. I muted myself so that I could tell my child to get his own bowl of chips, and then I forgot to unmute myself.
Do you need to restart the recording?
Nah, it's going. Now everybody in the world that watches this video will know that my child had to get his own bowl of chips. It's perfect. 10:30 a.m. bowl of Doritos. Healthy choices. All right. Jacob, are you back and can you see what I've written there now?
Yep, we're good.
All right, spectacular. If that happens again, just yell at me or type it in the chat and we'll figure it out. Or if I, start teaching while I'm muted, or who knows, if I do something else stupid, just let me know. All right, so restarting again. We are looking for the limit of our function f of x as x approaches a. That's what this notation means. It's the limit, LIM, the limit as x approaches a, that's just a little arrow, of f of x. And so what that means is, what y value does our function get very, very close to as the x values get very, very close to a? So in this case, we don't have an actual number written here. We just are saying that it's L. That's L. That's our limit. That's our limit, is this y value. So if I said that right here, this is 7, then I'd say, sure, then the limit of this function as x approaches a is 7. As x gets very close to a, y gets very close, or f of x gets very close to 7, gets very close to the limit. Note that we have an open circle here. We don't actually have to get to this number. We just have to get very close to it. And that's the difference basically between calculus and everything that you've dealt with in math before. You talk about what happens at a point, right? You're like, okay, here's my function. My function is x squared plus 3x plus 5. What does that function equal to when x is 1? And you plug it in and you find a number, right? That's kind of like a thing that you do. You're like, oh, okay, what are the x-intercepts of this function? What's happening at this specific point? Well, in calculus, we're no longer really going to be concerned about what happens at the point. We're going to be concerned about what happens as we get very close to the point. What does our function do? How does our function behave as we get very close to certain x values? Whether or not we actually get to a specific y value at x equals a doesn't matter. We care about what happens as we get very close to it. That's the whole idea behind limits. Good or no? Yeah? All right. So as we do some of this stuff today, we're going to be asking ourselves these questions when we talk about limits. If we can answer both of these two questions as yes, then we have a limit that exists. So the first question we want to ask ourselves every time we're looking into a limit is, as x gets close to a, does the function get close to some real number, L? And that's what we had in the picture before, right? As x got very, very close to a, the function got very, very close to L. Okay? So yes, question 1 was satisfied with what we were just talking about. The second part is, can we make our function get as close to L as we want by picking numbers that are closer and closer and closer to A? So what that means is, suppose I wanted this to be 6.999. Could I pick some value of x so that when I plugged that value into my function, I would get 6.999 with this function? Yeah. Could I get 6.999999999? Yeah, I could get as close as I possibly wanted to 7 by picking numbers that are very, very close to A. And if I can do that, then that means that the limit exists. And whatever that value that you're getting very, very close to is the limit. Does that sort of vaguely make some sense? Yeah, cool. So we're going to take a look at this with some very simple functions and some very easy continuous functions to start with. It either probably sounds perfectly reasonable to you and makes perfect sense, or it sounds completely confusing to you. And I'm going to clear that up for you in just a second if it sounds completely confusing to you when we start doing these simple, easy functions. We're going to see how easy it really is. So we're going to take a look at the function 2x minus 3. And I'm going to talk about what I wrote at the top there first. But before I do that, I'm going to graph the function y equals 2x minus 3 in Desmos. We're going to just take a look at it. I should be able to show it to you on my screen here if I'm capable of using my computer correctly. There it is. There's y equals 2x minus 3. And we were looking for the limit as x approaches 4. Is that right? I think I can't see my other screen. Yeah, the limit as x approaches 4 of 2x minus 3. So what we're going to do is we're going to go over here to 4, and we're going to say, well, what does my function get very, very close to as the x values get very, very close to 4? And what is it?
It's 5.
It's 5, right? It's getting very, very close to 5. As my x value gets to be like, let's say, watch, I'll zoom this in. As my x value gets to be like 3.999, I'm very close to 5. Or if I'm just on the other side of 4, 4.001, my y value is very, very close to 5, isn't it? Gets very, very close to 5. Could I get as close to 5 as I wanted to? If I wanted to be at 4.999999999 for my y value, could I find the x value that makes that true? The answer should be yes. If I want y to be 4.9999999, all I have to do to figure out the x is add 3 and divide by 2, right? And I could find an x value that gets me as close to 5 as I want. No matter how close to 5 you want to be, you can always find an x value that will get you there. Because of that, the limit exists. And so what we will note as we go through with some of these is that anytime we have a function that is continuous at the point we're looking at, the limit is just equal to the value of the function. So in this case, the limit as x approaches 4 of 2x minus 3 is just the value of the function. It's just 5. Because the function is continuous. 2x minus 3 doesn't have any breaks or gaps in it, right? It doesn't have any discontinuities. Continuous for all real numbers, isn't it? Yes, it is. You can respond to me when I say things. It's okay to respond. So this limit is 5. Any questions on that?
No.
All right. Hey, look at that. We got a response. I like that. All right. So what about the next one? X squared plus 1. Is this function continuous?
Yes.
Yes, this function is continuous for all real numbers. So its limit as we approach any value, in this case, -3, should just be the value of the function, which is 10, right? And if we were to go back in and take a look at this on Desmos, what do we have? We had -x squared plus 1, right?
Yeah.
Was it plus, what was it? -x squared plus 1?
It was just x squared plus
Oh, x squared plus 1. I don't know why I have a negative there. X squared plus 1. Okay. And as we approach 3, we'll see that the value of the function is 10. We can get as close to 10 as we want by plugging in, 9.99999 for the y and solving it for x if we wanted to. Okay. Continuous function, the limit is just the value of the function. What about this last one here? The limit as x approaches 7 of radical x plus 2.
3.
All right, and why should this be 3? Is square root of x plus 2 continuous for all real numbers?
Yes.
I don't think it is.
No.
No, it can't be less than -2.
Right. So this is what our function square root of x plus 2 looks like, right? But we're interested in at x equals 7. And if we look over here at x equals 7, there's nothing weird happening at x equals 7. It's just a continuous piece of the graph.
You didn't switch to
surrounding 7.
Desmos.
Oh, I didn't switch to Desmos. Thought I did. There we go. Now I did. So if I look over here at x equals 7 on our function, then the function is continuous surrounding x equals 7, which means that this same idea will apply. If the function is continuous at that point, then it's just the value of the function at that point. If I tried to plug in something like -3 into this, if I wanted to know what the limit as x approached -3 was, well, we couldn't do that because the function's not continuous at -3. There would be no limit there. But any value greater than -2, it's just the value of the function. Does that make sense?
Yes.
Cool. All right, anybody have any issues with this basic idea here that if we have a continuous function, the limit is just the value of the function at a?
No.
All right. Cool. So real quickly, tell me, if f of x is 2x plus 1, what's the limit as x approaches 3 of f of x?
7.
7, easy. 2 times 3 plus 1, 7. What about at -3?
-5.
-5. It's like you guys can do basic arithmetic. This is excellent. What about at 0?
1.
1. Yeah, easy enough. Any issues with that?
No.
Now you're all wondering why people said this class is difficult. It's not. It's a very easy class. See? You just do basic arithmetic and you should be good.
That's not true.
You don't know if that, it's probably true. All right, so let's look at this one. Nice and easy one. F of x equals x plus 2. What's the limit as x approaches 1 of f of x?
3.
3, easy, right? See, I told you this class was easy. Now, we're gonna make this slightly more complicated. This graph, x squared plus x minus 2 divided by x minus 1. So rational function, right? And you know how to graph rational functions, right? Yeah, first thing you always do is you factor them, right? So what is this factor to? It's x plus 2 and x minus 1 over x minus 1, right?
Yes.
Yeah, so because I have the same factor in the numerator and the denominator, I cancel those out and just put a hole at x equals 1. So this looks exactly the same as the graph of x plus 2, except with the hole at x equals 1. Everybody feel good about that graph?
Yes.
Yeah, so it's the same as what we were just looking at, right? X plus 2, except now I have a hole at 1. So my question for all of you is, what's the limit as x approaches 1 of this new function g of x squared plus x minus 2 over x minus 1?
Maybe 3.
What do you guys think? I got one person that said it should be 3.
I agree.
Agree. Anybody disagree with 3?
Agree.
Agreed. Yeah, everyone agrees with 3. Yes, you are right. This should be 3. Now, some of you might be sitting there not wanting to disagree, thinking that this doesn't exist. Well, it's true. The point, there's no point at 1, 3. That point does not exist. But we have transitioned now to calculus, which means we're not talking about what happens at the point. Most of the time, we're talking about what happens as we get very close to that point. So as x gets very close to 1, y gets very close to 3. Can I get all the way to 2.9999999 if I wanted to? If I wanted y to be 2.999, let's say, could I get that y value?
Yes.
Yeah, I just go back in and I'd set it equal to x squared plus x minus 2 over x minus 1 and figure out what x value gives me that. Okay? I should be able to make that work every time. I can get as close to 3 as I want. We feel okay about that?
Yeah.
All right. Let's take a look at this one. So we got a slightly different graph here. This is now a piecewise defined function. Got the same x squared plus x minus 2 over x minus 1 when x does not equal 1. So that gives us this whole linear piece, except without the point at 1, 3. And now I've got that our function equals 2 when x equals 1. So I've got an extra little point added in there. And now I want to know what is the limit as x approaches 1 of h of x?
it's still 3.
Still 3? Anybody disagree? Or does it not exist now that there's some other extra point in here? Or is it that point? Is it 2?
3.
3? I got 2 people voting for 3 here. Yeah, it's 3.
3.
Yeah, it's 3. Exactly. The whole point is we go back to these 2 questions. 1, as x gets close to a, but x does not equal a, does the function get closer to some real number? Well, yeah. As x gets very, very close to 1, my function gets very, very close to 3. Right? It doesn't have to get to 3. It just needs to get very close to it as I get close to 1. And can I get as close to 3 as I want? Can I get to 2.999999999? I can. I just have to find the right x value for that. Set this equal to 2.999999999, and I will get the x value that gets me as close as I wanted to 3. Okay. So we'll note that 3 different things were happening here. In the first function, in f of x, f of 1 was equal to 3, and the limit was also 3. In the second one, g of 1, or well, g of 1 actually was undefined or did not exist. And in h of 1, we got 2. But in all 3 of those cases, the limit was still 3. So the function can exist at the point, the function cannot exist at the point, and the function can have a different value at the point than the limit. But it doesn't mean that the limit changes. And you see how all that works or no? Everybody feel okay about that?
Yes.
All right, excellent.
Yeah.
Everyone's good, no questions. All right. Let's take a look at this one. This is a fun one. Sine x over x. We want to find the limit as x approaches 0 of this. Any thoughts?
1.
If you look at the graph, like it makes sense. If you, I would say, if you look at like
Yeah. Equals to 1.
think about plugging it in, you can tell that it's undefined at that point.
All right, yeah, so I think I could hear a couple people saying 1, and then somebody was saying that it looks like it should be 1, but the function is actually undefined there. Right? There's actually a hole right here at x equals 0. So it's hard to sort of tell what's going on here. Now, I'll tell you this, the answer to this is 1, but we can't be sure of that without having some algebraic way to figure it out. Even if we were to look at the graph, and I'm going to pull up the graph of this on Desmos for you to take a look at. All right, here's sine x over x. We know that it's undefined here, even though it doesn't show it, because if I plug in 0 for x, sine of 0 is 0. And if x is 0, we end up with 0 over 0, which is, what is 0 over 0 called? Anybody know?
Indeterminate.
Hey, somebody has been learning something. This is good. Not from me, but from somebody else. This 0 over 0 is indeterminate. Okay. It's not undefined. It's not, does not exist. 0 over 0 is indeterminate. And there are lots of other things that are indeterminate, but this is the big one that we're going to see all the time is 0 over 0. And when I look at my graph here, I could zoom in. You guys are back on the graph now, right?
Yes.
Okay. It does look like it's approaching 1, doesn't it? Certainly looks like it's approaching 1.
Yes.
Yeah. But we could zoom in here forever, and I can't quite get this centered like I'd like it to be, but I could zoom in here forever at 1, and it doesn't look like anything weird is happening here. It doesn't look like it's shooting up to an asymptote or shooting down to an asymptote to where it's not actually approaching 1. But we can't be certain of that without doing some algebraic work to figure that out. And we're going to do some of that algebraic work later today. But it sure looks like graphically this is 1. And oftentimes you're going to have to, on the AP test, just use a graphing calculator to estimate what the limit of something is. And you can't be sure, but you can get a pretty good idea by zooming in on the graph. Either, you know, if you're sitting there on the AP test, you could use Desmos if you're at home, but otherwise if we make it back in the classroom this year, I'll show you guys how we can do all that on the graphing calculator too. So far, good?
Did you explain how to do it algebraically?
Yeah, we're going to do it in a little bit. We're not actually going to do it quite yet, but we will do it hopefully later today. We're going to do some easier ones first, algebraically, and then we'll get to this one. This one's a little bit more complicated. So hold off on that for a minute, and I promise we'll get to it. If we don't do it today, we'll do it tomorrow for sure, but it's down the notes somewhere today. All right, so let's take a look at this one. This one we got x cubed minus 2x squared over 3x minus 6. And I've drawn the graph for you here already. So I want you guys to think about what you think the limit as x approaches 2 of this is. So on your own computer or on your graphing calculator, graph this function and zoom in at x equals 2 and see if you can come up with an idea of what that is while I deal with my 7-year-old for 1 second. I'll be right back. All right. You guys get an idea of what you think that is? I got somebody typing in the chat. Let's see here. 1 1/3. Okay, 4/3, 1 1/3. Anybody else got that, or somebody got something different guess of what it is? It sure looks like it could be that, right? So if you zoomed in on your graphing calculator, you could be looking at the table. You guys know how to look at the table on your graphing calculator?
Yes.
Yeah, so go into the table and you can sort of just keep going in and looking at it. So we got a positive infinity as one option here. So we got 1 1/3, we got positive infinity. Anybody else have a different idea? No? Okay, so let's see if we can algebraically figure out how to figure out what this is. So what we're going to do is we're going to say the limit as x approaches 2 of f of x is equal to the limit as x approaches 2. And it's very important that every time you write this out, you include the limit at the beginning, limit as x approaches 2. And we're going to factor this numerator. What can I factor out of the numerator?
X squared.
All right, take an x squared out, which leaves me with an x minus 2. And I can take out a 3 from the denominator, which leaves me with an x minus 2. And we'll note that we have an x minus 2 and an x minus 2 in the numerator and the denominator. Those are going to cancel out. So we're going to say this is the same as the limit as x approaches 2 of just x squared over 3. So far, good? Then we plug in the 2. When we plug in the 2, we no longer need to write the limit part of it because we're evaluating this function, this new function at x equals 2 to get us 4/3. So it looks like the answer is 4/3, and that's what it is. This is algebraically how we would complete one of these. Does everybody see that process? See those steps easy enough? Feel okay about that?
Yes.
Okay. Perfect. So let's look at another one. We just did that. Let's look at another one here. Anytime we're evaluating a limit, the first thing we want to do is we want to plug in this value and see what happens. And so I'm going to, before this unit on limits is over, I'm going to write out a whole list of things that you should always be doing with limits. But the first thing you should always do with limits is plug in the number. So plug in this 2 and see what happens. So we're going to do this without bothering to graph it. Graphing is kind of a pain. What happens if you plug in 2 to this? What do I get in the numerator?
0/0, so it's indeterminate.
Right, we end up with a 0 over a 0, right? We get I think an 8 minus 10 plus 2, which is 0. And we get 20 minus 14 minus 6, which is 0. We get an indeterminate value, okay? Which is okay. It's not great. We'd rather not get an indeterminate value because if I got like 7 when I plugged in 2, then my answer is just 7. And if I got negative 4/3, then my answer is just negative 4/3. But I got this 0 over 0. I got this indeterminate thing, which is a problem, which means we got to go in and we got to try and factor each of these out. So take a couple seconds and factor both the numerator and the denominator, cancel out your common terms, and see what you get. And then I'll go through and do it with you guys after you've given it a try on your own. I'll give you about a minute to factor those and cancel and get an answer. All right, what do we factor that top to be?
X minus 1.
2x minus 1 and x minus 2? Does that sound right? Yeah. And the bottom to x minus 2 and 5x minus, oh, sorry, 5x plus 3? Yeah. We lose those x minus 2s, and we end up with 3 over 13. Good or no? Everybody go with that? Yeah? All right, so when we get these nice, simple, rational functions that end up being indeterminate, 0 over 0, all we gotta do is factor, cancel, and get an answer. If the function didn't turn out to be indeterminate, then we plug it in and we get an answer. We're done, right? Like those first few that we did where there was, it was just 2x plus 1 and we were plugging in the numbers, or x squared plus 1 and we plugged in negative 3. The easy way is to find limits, to find out what's happening as we approach that value. All right. This one's a little bit more difficult, but what's the first thing we should do with it? It's a limit, so what do we need to do first?
Plug it in.
Plug it in. Plug in the 9. What happens when I plug in 9? You get 0 over 0. So that's a problem. Yeah? Once again. How are we going to solve that problem?
you could rationalize the denominator.
All right, one option, rationalizing the denominator. That's what we're going to do. First, we're going to do this two different ways. So one option is rationalizing that denominator, which means what do we need to multiply the top and the bottom by?
Root X
Square
minus-
root of x plus 3.
Yeah, so that's the conjugate of the denominator, right? So we got x minus 9 times square root x plus 3. And then in the denominator, we got square root x minus 3 and square root x plus 3. And we'll simplify that denominator. We're going to leave the numerator as it is, but we can simplify the denominator. What do I get if I distribute all that out in the denominator?
X minus 9.
You just get x minus 9, which will cancel with the x minus 9 in the numerator and gives us just the limit as x approaches 9 of root x plus 3, which is 6. Everybody see how we did that? Any issues with that? All right. Another option that we could have used is we could have just factored the numerator straight away from the beginning. We could have noted that 9 is a perfect square, right? It's 3 squared, and x is a perfect square. It's root x squared. So this is really just a difference of squares. I could have factored the numerator into root x plus 3 and root x minus 3. The root x minus 3s would cancel, and we'd end up with the same thing, root 9 plus 3, or 6. So either way, we get the same thing. One way by factoring, the other by multiplying by a conjugate. But it's important to remember the idea of multiplying by the conjugate or rationalizing that denominator, because it is a helpful trick solving some of these indeterminate limits. So far, good?
Yeah.
Any questions?
No.
No, everybody's good. All right. We have plenty of time left, right? We still got like 20 minutes or so, I think. So we're going to get some more stuff done here. Let's take a look at this one. The limit as x approaches 0 of 1 over x. We want to know why this doesn't exist. I'm telling you right off the bat, it doesn't. So how can I show that this doesn't exist? Let's do it graphically. What does the graph look like? Describe the graph to me in the first quadrant. What should it look like?
An asymptote.
Should have an asymptote at the y-axis, and it should have an asymptote at the x-axis, right? It's imperfect, but it should look like that up there in that first quadrant. Is there anything going on in the second quadrant?
No.
What about the third quadrant?
Yep. There's another asymptote down there.
Yeah, another basically looks the same as the first quadrant except mirrored over. And what about the fourth quadrant?
No, nothing there.
No, okay. So why do we know that there's no limit as x approaches 0?
Oh, because the two arrows as they approach x, they're going different ways.
Right, as we go towards 0, this one's going up, right? This one's going up towards infinity, the one in the first quadrant, and the one in the third quadrant is going down towards negative infinity. They're not even approaching a specific numeric value. And a limit, for a limit to exist, always has to approach a specific numeric value. And so this limit can't exist. From one side, it's approaching a positive infinity, and from the other side, it's approaching a negative infinity. Okay? And we could have known that by just plugging this in at the beginning, and we get 1 over 0. We know that 1 over 0 is undefined, right?
Mm-hmm.
And so if we get something that's undefined, we know that that limit doesn't exist. Whereas if we get something that's 0 over 0, if we get something that's indeterminate, then it could possibly exist. Right? So far, good? All right.
Yeah.
Let's look at this one. So here's what I'd like you to do. I'd like you to, on Desmos or on your graphing calculator, take a look at this graph and see if you can come up with a reason why this limit doesn't exist. I'll give you a minute or two to look at that and think about it. So either get your graphing calculator or Desmos and graph the sine of 1 over x. And I'll throw it up on Desmos here for you to take a look at also. Here is sine of 1 over x on Desmos. So think about why that limit might not exist as x approaches 0.
I mean, I'm assuming it goes up and down infinitely. So there's really,
It looks like it goes up and down infinitely, right? But can we be sure of that? How do we know for sure? All right, I got 1 over 0 is undefined algebraically. This is true. So the Nadine, right? Yeah. The question then is 1 over 0 is undefined, but 1 over, we're not actually doing 1 over 0, right? We're looking at what happens as we get very, very close to x equals 0, which is we get very, very close to x equals 0. What's happening to this? What's happening to 1 over x? If x gets very, very small, like 0.000001, what happens to the number inside of the parentheses, inside the argument of our sign?
It's becoming super big.
Right, it's becoming very, very large, right? 1 divided by a very, very small decimal is a very, very large number. And so we plug in a very, very large number in here, the sign of a very, very large number exists, doesn't it? I can take the sign of anything, can't I? So it becomes a little bit of a question. But it does certainly look like, if I zoom in on this, besides like, well, now you can't see it, but besides it kind of getting a little bit trippy there, like you're going into some sort of vortex or something, it sure looks like this thing is oscillating back and forth and back and forth and back and forth infinitely, doesn't it?
mm-hmm.
Yeah. So we'd like to show that that's true, because if it keeps oscillating up to 1 and then back down to -1 and then back up to 1 and back down to -1 an infinite number of times in here, because that's kind of what it looks like it's doing, can it possibly be approaching some number?
No.
No, if we go up to 1 and we go back down to -1 and we go back up to 1 and we go back down to -1, I'm not getting closer to any one particular number as I get closer to x equals 0, am I?
No.
Yeah. So any ideas on how we could prove that this oscillates back and forth infinitely? No ideas on that? When does the sine of 1 over x equal 1? Any thoughts on that? No? What angle, when I take the sine of it, gives me 1?
90 degrees.
90 degrees, or if we do it in,
1/2.
yeah, pi over 2, right? Pi over 2 radians. So if my angle, what's my angle here? My angle is 1 over x, right? So if 1 over x were to be equal to pi over 2, then that would work, right? And that's, Chris, I think you said that in the chat there is 2 over pi, right? That would give us 1. But is pi over 2 the only angle that will give us 1?
No,
No, there's
But any
there's
multiple?
for 2.
right, any multiple of this by adding what to it?
Pi.
If I add pi, it's going to give me -1, right?
2
So
Pi.
I gotta add 2 pi, right? Well, I can't, I mean, not just 2 pi though. What if I added 4 pi
Second one.
and 6 pi and 8 pi, 2 pi n, right?
Yeah.
This is something you should have hopefully done last year in some of your trig stuff at the end of the year, I hope, is solve some equations like these.
Mhm.
So if 1 over x equals pi over 2 plus 2 pi n, where n is any integer, then that should give us a place where that graph hits y equals 1. And we can solve this for x, right? This just becomes x equals, we take the reciprocal of each side. We end up with this, right? And what happens as I plug in values of n in here for integers? So let's say, for example, I plug in n equals 0. What do I end up with? I end up with 1 over pi over 2, which is 2 over pi, right? What if I plug in n equals 1?
Over 5.
Yeah, I should get pi over 2 plus the 2 pi, which is 5 pi over 2, or 2 over 5 pi. What about the next one? Plug in n equals 2, I should get
2 over 9.
2 over 9 pi, right? And so on, right? And I just keep going on. I'm going to get 2 over 13 pi and 2 over 17 pi and 2 over 21 pi. And what can you tell me about each of these? 2 over pi, is that bigger or smaller than 2 over 5 pi?
Bigger. Wait.
Yeah,
Yeah.
2 over pi is larger than 2 over 5 pi, right? This is, I mean, pretend the pi is just a 3. This is 2/3 and this is 2/15, right? 2/3 is more than 2/15, which is more than 2 over 27, approximately, right? And each of these is going to get smaller. And where are these going to get closer to? These are going to approach
0.
0. They're going to get smaller and smaller. They're going to approach 0. But how many of these are there going to be?
Infinite.
An infinite number of them, because n is any integer, right? And there are an infinite number of integers going up. So we have an infinite number of times when this function hits y equals 1. And if we were to do this the other way, using -1, let's say when the sine of 1 over x equal -1, well, we know that that 1 over x should then equal 3 pi over 2 plus 2 pi n. And x would be 1 over that. And how many of these are there? There are an infinite number of these also, right? Do you guys agree that there's an infinite number of these since there's an infinite number of
Yeah.
integers? Yeah, and these are also going to be approaching 0.
Yes.
And so what we're proving here is that there are an infinite number of times as I go towards 0 that this function hits 1. And there are an infinite number of times as I go towards x equals 0 that this function hits -1, which means that this oscillation that we see in the graph happens an infinite number of times as we go back and as we go towards x equals 0, which means that as I go towards x equals 0, it's not zeroing in on some specific value. It's not zeroing in on y equals 0 or y equals a half or y equals 1. It's not getting closer to that. It's going back and forth and back and forth. And so no matter what, there's no way to get close to one specific value as we get closer to x equals 0. Does that make sense? And so algebraically, that should show that there are an infinite number of oscillations. And therefore, we can't approach a specific value, and that's why it doesn't exist. Does that make sense? Anybody have a question on that?
Could you also show it, because as you get like closer and closer, x gets to be a smaller and smaller number towards 0, and since it's over 1, that would like effectively make it like sine of infinity, which is also just undefined.
Yeah, I mean, generally that's true, but that's not a solid algebraic proof of it. But I mean, you've got the right idea.
Okay.
Yeah, that makes sense, yeah.
Wait, is it because that it's infinitely oscillating that you can't get to a specific point?
That's correct, yeah.
Okay.
Yep. Okay, I'll give you guys a second to read over this. We're going to talk about left hand and right hand limits, which kind of go hand in hand with what we've been talking about. Left hand and the right hand limit are going to be very important to what we deal with this year, because without those, we can't really have limits in general. So take a look at what this says.
I think you muted.
All right, sorry, I had to make sure my kid brought his laptop back inside after he was pogo sticking for his teacher, because it started raining at my house unexpectedly. I'm not sure why, but it'd be unfortunate if like the first day of real school, he left his laptop out in the rain, you know? So we talk about left hand limits and right hand limits. A left hand limit is the same as the regular limits we've been doing, except it just means that the function has to exist to the left of the number that we're looking at. And a right hand limit, the function just has to exist to the right of the number that we're looking at. Other than that, the whole process of looking for the limit is still exactly the same. So the only difference is the notation, and you'll see that I've got a minus sign here. Right? That's a left-hand limit, means it's coming from the left side, and a right-hand limit means it's coming from the right-hand side. It's got a little plus sign. Okay? As long as we've got an open interval to the left, we can have a left-hand limit. As long as we've got an open interval to the right, we can have a right-hand limit. So we're going to take a look at the graph of the square root of x minus 2 and see if we can figure out these limits. So the square root of x minus 2's graph, I know it's not perfect, but it generally looks like that. So if I'm talking about a right-hand limit for this function, which is what the first one here is, the limit as x approaches 2 from the right of f of x, what should that equal? What y value am I getting close to?
0.
0, exactly. As I approach x equals 2 from the right, I'm getting very close to a y value of 0. Okay. What about as I approach 2 from the left, from over here?
There's no function, like the function doesn't exist there.
Right, the function doesn't exist to the left of 2. And since there's no open interval to the left of 2, we say this does not exist. Good or no? Okay. And so now what if I ask you what's the limit as x approaches 2 of f of x?
The limit doesn't exist because from the left and the right, that they don't meet at one point.
Exactly. So an important rule about left and right hand limits is that the left hand limit and the right hand limit have to both exist, and they both have to be the same value for the actual limit, which technically is called a two-sided limit. For this two-sided limit to exist, both the left and the right hand limits must exist, and they must be the same. And so that's this very important rule here. The limit as x approaches a of f of x equals L if and only if the limit from the left and the limit from the right of f of x are both equal to L. Very important rule. So if you're taking notes on stuff, you want to write that one down.
Are left and right hand limits used when like there's a fixed point on one end of the graph instead of like two infinite arrows? Is that when they're used, or are there other?
There's other uses of it too that we'll see, but that is one use also. Like the one we just did, you know. This one we can only look at the limit from the right, so that's what we would use for this particular one because that's all we've got at 2. But they're used in other cases also, which we'll see as we kind of move through this unit.
So if x was approaching 6, then would it be possible like from both sides?
For the root x minus 2 graph, for this one? Yeah, definitely, yeah. So if I asked what's the limit as x approaches 6 from the right or 6 from the left, it's just going to be 2 for both of those, which makes the two-sided limit also 2.
Great. Thank you.
What if for the left side and the right side, they are both going towards like a number like infinity?
So we're going to get more into infinite limits. So suppose they were both going towards positive infinity.
Positive infinity.
Yeah, let's say they were both going towards positive infinity. Technically, we would still say that that limit doesn't exist. We would generally notate it as this limit is infinity. But one thing I'm going to make a note of when we talk about infinite limits, probably tomorrow or the next day, is that a limit has to be a whole, or not a whole number, but a real number. It can't be an infinite thing. It can't be infinity. The limit has to be a real number. It has to be approaching a real number. Does that make sense?
Yes, that makes sense.
Okay, cool. All right, I think what time does this class actually end? By like no, we still got 4 minutes. All right, we're gonna do this last problem. We're gonna stop on this one, then we'll be done. So here's the graph of the absolute value of x over x. This is a graph that you may or may not be familiar with, but you should become familiar with now. Know what this graph is. You know what a parabola looks like. Like you know how to manipulate x squareds or like square root function or an absolute value function or the cubic functions. Well, this is another one of those that you should just know. This pops up all the time on the AP test. Is the absolute value of x over x. And it's just looks just like this. We got horizontal line to the right at 1 and to the left here at -1. And at 0, at x equals 0, we have open circles on both sides. So if I plug in 0, I get 0 over 0. I plug in any positive number, I get 1. I plug in any negative number, I get -1. Okay. So what's the limit as x approaches 0 from the left of this function?
-1.
Should be -1 because that's what the y values are equal to as we are to the left of x equals 0. And what about as we approach 0 from the right?
+1.
+1, which means that the two-sided limit
Does not exist.
does not exist because the limit from the left and the limit from the right are not the same. Good?
Yep.
All right, cool. We'll stop there so you guys have a little extra time to get to your next class for the day.